cope with it. So here's a quick summary of the main vibratory ground improvement methods, again with a focus on deeper compaction. And so the original one is vibrocompaction, often referred to as VC, and it's where you've got a vibrator, often referred to as a vibraflot, that's lowered down into the ground, often with the aid of water flow, and the vibrator vibrates the ground and densifies it. To create a densified column, and then you move over and you repeat this on a reasonably close spacing. And then there are stone columns, and so that's been broken down to stone columns by vibro displacement, and that's where gravel or stone is added via a tremie pipe and supported by compressed air or water, and then the soil is laterally displaced, as you see in the little diagram below. And then there's stone columns by vibro replacement, which is gravel is added via a washed out space around the vibraflot, and soil is partly laterally displaced as well as partly replaced. And you can see the picture on the left of the equipment and a slightly different image of the vibraflot creating the void, and then the void being filled with stone or gravel, and then the vibraflot being used to densify the stone and gravel as you build a column, a stone column. Then there's dynamic compaction, originally developed in France, I think by the Maynard group. And essentially this is conceptually quite simple, where you drop a large weight from a height, and this weight falls on the ground and therefore, of course, compacts the ground, as illustrated in this diagram by the left and the photograph on the right. It's quite impressive to watch. These weights can be quite large, and they can be dropped from very large heights. And often there is a series of drops done, initially a first one, and then coming around with a secondary one to sort of fill in the gaps. And you can see the illustrated effect of the compacted ground with some working platform. And then for sort of more shallower environments, there's these rammed aggregate piers that have become quite popular. They tend to be shallower, often less than about 12 meters, you have become quite popular for shallow ground improvement. And then also more recently, a number of sort of surface compaction techniques. This one's illustrated as rapid impact. And so although I'm talking primarily about deep compaction, the principles still apply to these shallower techniques. So the vibro compaction, vibro replacement tends to be much deeper, can go really quite deep, up to 30 meters. Dynamic compaction varies in depth depending on the ground conditions, and then things like the rammed aggregate piers and rapid impact a little bit shallower. So the quality control for ground improvement, CPT is increasingly used for quality control, and that's because, of course, it's fast and cost-effective, gives you a continuous profile. The measurements are very repeatable and reliable, and more importantly, you get more than one measurement. So unlike the standard penetration test, which used to be popular, which just gives you a single blow count, the CPT provides a range of measurements from tip resistance, the sleeve resistance, the pore pressure, and increasingly adding on things like shear wave velocity, and we'll talk about that later. So the CPT in granular sand-like soils is influenced by, of course, the density or state of the soil, the in-situ stresses, the stress history, but also the grain characteristics such as the mineralogy, the compressibility, and fines content, and also a little bit due to the microstructure in the ground, which can be factors such as age and cementation. So this is just a reminder of what the cone measures, and here you can see the diagram of a standard cone penetrometer, and there's a load cell that measures the force on the tip, and when that load is divided by the cross-sectional area, you get the tip resistance in units of stress. And then there's a second load cell that measures the load of the soil as it passes this friction sleeve, and when that's divided by the surface area, it gives you the sleeve resistance in units of stress. And then there's quite often a saturated porous element and a pressure transducer that measures the water pressure, typically behind the tip in that U2 location. So you can measure tip, friction and pore pressure essentially continuously while the probe is pushed into the ground. Now, we've discussed in previous webinars that because soil is controlled by, soil behavior is controlled by the effective stress in the ground, then ideally we need to normalize the cone data in terms of effective stress. And Professor Roth, way back in '84, was the first person to really strongly suggest this. And so these normalized parameters essentially stem from that early work. And so there's the normalized cone resistance, which is the net cone resistance, the cone resistance minus the total overburden pressure divided by the effective overburden pressure. And when Professor Roth suggested this, it was primarily for clay soils, and you'll see in a minute that we've slightly modified that to be applicable to a wide range of soils. And then there's sort of the generalized normalized friction, which is the sleeve friction divided by the vertical effective stress. But it's become quite popular to use the friction ratio, which is the ratio of the sleeve friction divided by the net cone resistance in percent. And then if you measure pore pressure, there's really two normalized pore pressure parameters. The initial one was the excess pore pressure, which is the measured pore pressure minus the equilibrium piezometric pressure at that depth, sometimes regarded as the hydrostatic, divided by the net cone resistance. Or more increasingly, Schneider and others have suggested that a normalized pore pressure parameter of the excess pore pressure divided by the vertical effective stress. So you can see that the more popular parameters now in some respects are the Q, F, and U as the normalized parameters of normalized tip resistance, friction, and pore pressure. Now, the normalized parameters have become quite popular to identify soil type, or more correctly, the soil behavior type. And so here's the normalized chart that I had suggested 25 years ago. And so it's the normalized cone resistance on the vertical axis on a log scale, and then the normalized friction ratio on the horizontal scale, also on a log scale. And generally, sands have high tip resistance and low friction ratio, and clays tend to have a lower tip resistance and higher friction ratio, and the mixed soils tend to plot in the middle. And there's a zone identified down the middle of the chart where most sort of normally consolidated young uncemented soils tend to plot, and there's arrows indicating that for clay soils with increasing OCR the tip resistance tends to increase, and with increasing sensitivity the friction ratio tends to decrease. And for sands, increasing normalized tip resistance is a sign of increasing relative density, and if the data moves diagonally up to the right, that's generally a sign of increasing stress history, age, and/or cementation. But the key thing to note here is that the soil behavior type is based on the in situ behavior of the ground, which is reflected in the strength, stiffness, and compressibility as measured by the cone, which is not exactly the same as those traditional classification systems that we tend to be used to in geotechnical engineering, which are based on physical characteristics, based primarily on Atterberg limits and grain size distribution on disturbed samples. So there is a little bit of a difference between the soil behavior type and the traditional classifications based on physical characteristics, such as grain size and Atterberg limits. And in fact, our next webinar early next year will be a discussion on sort of updated approaches for determining the classification of soils. And so we'll go into this in more detail in our next webinar. But this normalized soil behavior type chart has become quite popular. And then one of the features that Jeffries and Davies had identified also over 20 years ago was that they had recognized that these boundaries between the various soil types were roughly concentric circles when plotted on this log-log chart. And they suggested that, that you could capture these boundaries by identifying this soil behavior type index IC, which is simply just the radius of an imaginary circle. So there's a center of a circle up here. And if you combine the normalized tip resistance and normalized friction ratio to calculate the radius, if the radius is small, you're up in the sandy region, and if the radius is high, you're down in the clay region. So it combines these two measurements into one, and it's an index of soil behavior. So if IC is rather small, up around 1 or 2, it's typically sandy soils, and if it's up around 3, it's typically a more clay-like soil. Now, IC is primarily a function of soil compressibility, and compressibility is linked to the plasticity of the soil as well as the amount and type of fines, and we'll discuss that a little bit later. Now, about 5 or 6 years ago, I sort of suggested that we needed to update that normalization and suggested a more generalized normalization. I know it looks a bit complicated here, but it's the net cone resistance divided by atmospheric pressure to get a dimensionless net cone resistance multiplied by this stress normalization factor, which is the atmospheric pressure divided by vertical effectives to a stress exponent, where stress exponent varies with soil type as well as stress level. In simple terms, in clays, the stress exponent of 1, and so this drops back to the original form that Roth had suggested. But in sands, the stress exponent tends to be more towards a half, and so it reflects the nonlinear increase of tip resistance with effective stress, which you tend to see in sands. So this is referred to as QTN, N being where you've got this variable stress exponent N. And so the chart that we use now is the same chart, but now it's got the QTN on the vertical axis. And this is to illustrate that since the vibratory techniques used for ground improvement mostly work in coarse-grained sandy soils, this illustrates the zone of which coarse-grained sandy soils tend to fall. And you can see it represents by that original boundary, which can be approximated by the IC of 2.6. You can see in the sort of normally consolidated range for most young, uncemented, normally consolidated soils, an IC of 2.6 is very close to the original boundary. When you get off into the sort of more over-consolidated, stiffer soils, the IC of 2.6 is not an exact fit, but it's close enough. Now, there's been quite a bit of work on what sort of soils are compactable using vibratory techniques, and there's quite a well-known book on ground improvement by Kirsch and Kirsch, and they have a nice plot that illustrates the change in normalized tip resistance as a function of fines content. This is the diagram on the left, and so there's some data before improvement, pre-improvement, and then data after improvement, the post-improvement data. And you can see the tip resistance shows a significant increase, at least when the fines is quite small. With increasing fines content, the materials become harder to compact, and you see less of a change in the tip resistance with compaction. And basically, it sort of shows that once fines content gets up around 40%, it typically gets harder to compact. Although fines content itself is not the best indicator, so the diagram on the right suggests that if you've got the normalized tip resistance as a function of this soil behavior type index, the data plots a little bit better, and you can see that before compaction the numbers are quite low, and then post compaction they get quite a bit higher. And again, once you get IC up around 2.5 or 2.6, it becomes harder to compact. And here's another plot. This is from Willie Dagan about 10 years ago. Same sort of plot. On the left, it's in terms of friction ratio, and on the right, it's in terms of soil behavior type index. And you see the friction ratio is rather a poor indicator. It's not as good as IC. IC, the data tightens up a lot more. And so if you look at the right-hand plot, you can see there's a very clear trend of increasing compactability when IC is quite small, and then when IC gets up around 2.6, obviously the ability to compact the soil becomes much more difficult. And that was one of the reasons behind that is the link between compactability and fines content. The difficulty with fines content is that it's really the plasticity of the fines that controls, and more highly plastic fines limit the ability for fiber compaction techniques to be effective. And so fines content alone does not really distinguish between plastic and non-plastic fines, and that's why IC is quite a good approach, because it captures both the presence of the amount of fines as well as the plasticity. And it's illustrated here on the left, where there's a number of correlations of trying to link IC with fines content. We had done that back in '98, that's the blue line, and recently it's been updated for various liquefaction studies. The black line is the one suggested by Bollinger and Idris, and the purple line is from Robertson et al. From Christchurch in New Zealand. And you can see them scatter, and so if I take 2.6 as an example, if you come across, you can see that the fines content can vary from as low as 10% to as high as 100%, depending on the plasticity of the fine. So these relationships tend to be average ones, and you can see that the ones for liquefaction tend to be biased more towards the low plastic fines, where liquefaction tends to be more of an issue. But this is just to illustrate that IC is a better measure of the combined effect of the amount and type of fines than just fines content, and that's why we see in this previous plot why IC, the data clustered so much better in terms of IC than it did in terms of friction ratio or fines content. And so this diagram is sort of an update of one that was first suggested by Professor Rainer Massage, where he sort of identified the zones of compactability on the soil behavior type. So this is the updated normalized soil behavior type in terms of normalized cone resistance against normalized friction ratio. And you can see that the sandy soils are predominantly very compactable. Of course, when you get into very dense sandy soils, they're already dense and so become almost impossible to densify anymore. So there's an upper boundary. And then there's a region where you sort of begin to get harder to compact, and then eventually you get into the more clay-like region, which is in fact not compactable using vibratory techniques. So in the past, quality control criteria was often based on relative density. That was always the traditional approach. And as we know, relative density is really the void ratio of the soil relative to its maximum and minimum values. And of course, even determining those maximum and minimum values can be quite problematic. And we also know now that really strength and stiffness is not always well represented by relative density, because it's influenced by the amount of fines and the stress level, and so there's a move away from using relative density. But most of the early relationships between relative density and the CPT were developed based on large calibration chamber testing on clean sands. And that's illustrated in this diagram. On the left, you see a sort of schematic, a nice diagram that Professor Main put together, illustrating how the work was done. These large calibration chambers where artificial sand deposits were placed under known conditions of relative density and stresses, and then the cone was pushed in to develop the relationship between the tip resistance and the depth as a function of relative density. On the right, you can see here that you see these curves get generated for a given relative density. The cone resistance increases and increases non-linearly. And so that's how this concept of normalization came about, is the cone resistance varies with depth, and so there's a need to sort of normalize or correct it as a function of depth, and normally it's corrected to 1 atmosphere of stress. So if you look at this traditional plot of cone resistance against vertical effective stress, then at 1 atmosphere of vertical stress, that's how you pull off the normalized cone resistance. And the fact that these are slightly curved is why the stress exponent is not 1. If the stress exponent of 1, this would be a linear increase, but we know that it's slightly nonlinear, which is why that stress exponent is less than 1. And these diagrams have been around for a long time. This is one taken from Professor Main again. So it's a plot of relative density on the vertical axis against the log of normalized cone resistance. And you can see here's a plot of many different relationships, all plotted on 1. And way back in the early 80s, we had suggested that it was a function of compressibility, and the scatter here is mainly due to the compressibility of the soil. But you can see that there's a lot of uncertainty if you go the relative density approach, that if you specify some given relative density for ground improvement, it's a little bit vague about what the normalized cone resistance should be. So there's generally a move away from specifying relative density and just simply specifying normalized cone resistance. And so you're tending to see now that people are specifying, have specified, say, a cone resistance profile, which can be analogous to a constant normalized cone resistance. So you often see people where they'll draw this simplified linear relationship that tries to reflect this constant normalized cone resistance. The difficulty with this, of course, it's a function of the unit weight of the soil and where the water table is. And so if you've got a site where the water table varies significantly, then this tends not to work very well. And so in general, it's not recommended to go this approach because it only applies to clean sands. So if you've got sands with fines, this is not going to work very well because it's essentially based on that correlation with relative density, which only applies to absolutely clean sands. So what do you do with soils when they've got fines? So the ground improvement vibratory techniques are generally less effective in sandy soils with high fines contents, and it depends on the plasticity of the fines. And that the penetration resistance, whether or not it's CPT or SPT, tends to become less sensitive in soils with high fines content. And so the trend should be towards using something like a clean sand equivalent, which I'll explain here. And the origin of clean sand equivalent really came about from the early work of Professor Seed at Berkeley when they were looking at liquefaction case histories, and they observed that soils with the same cyclic resistance ratio had different penetration resistances, whether or not it was SPT or CPT, as a function of a different fines content. So it was based on those case histories that this concept of a clean sand equivalent, in other words, the measured normalized penetration resistance corrected to an equivalent clean sand value. And of course, most of the case histories were liquefaction case histories, so these were mostly young, uncemented silica-based soils, and these are soils with little or no microstructure, and I'll explain what that means a little bit later. Sorry for the few typing errors on the bottom there. So how did clean sand equivalent come about? And really when we developed the CPT-based liquefaction method, Catherine Wright and myself, what we did is we looked at case histories for sizes of earthquakes, and that enabled us to draw essentially contours that would divide soils that liquefy from soils that didn't liquefy for given sizes of earthquakes. And essentially we produced contours of cyclic resistance ratio, which were essentially contours of this clean sand equivalent. And so you can see they're curved, and so you can have two different soils, say a clean sand up here that would have a given cone resistance and a given resistance to cyclic loading, and then say a siltier sand that would have a very different cone resistance, much smaller, but the same resistance to cyclic loading. And so we had developed this simple correction KC to take the measured normalized cone resistance, correct it to a clean sand equivalent, and the correction was just simply based on the soil behavior type index, since the soil behavior type index increases as you go diagonally down the plot. So what's the theoretical framework behind this? I mean, that was all based on observations with case histories. And if we look at some theoretical framework, if you use critical state soil mechanics and the state parameter approach that was particularly suggested by Bean and Jeffries and back in the early 80s, and they've got a very nice book that came out in 2006 that talks about this in great detail. And so it's built around the concept of critical state, where you have a critical state line in a stress space like void ratio against log of mean normal stress, and the difference in void ratio from the void ratio at its current state level relative to that at critical state defines the state parameter. And of course, they simplified it to a straight line over a limited stress range, but more correctly, it is actually curved, which Jeffries and Bean talk about in their book. But here I'm just illustrating the sort of the relative state parameter index that Professor Bollinger suggested. And here they've got that generic curve, and you see that same straight line. So at relatively low confining pressure, now this is up to 10 atmospheres, a straight line is a reasonable an approximation to the curve. And based on all that work that Bean and Jeffries have done on state parameter, has essentially come up with a simple screening approach where, based on both theoretical work as well as field data using frozen samples from the field, we were able to develop a set of contours of constant state parameter on the normalized soil behavior type. This was first suggested by Pluis et al. In '92, and it's been updated. I updated it a little bit, particularly to put it onto this normalized chart that's got the updated normalization. And so soils with the same state have the same behavior. So these two soils marked in red, they've got different cone resistances, different IC values, different friction ratios, but they essentially fall on the same contour of state parameter, so they have the same behavior to loading. These are essentially contours of dilatancy or dilation angle. And they apply primarily to young, uncemented silica-based sands, which I'll talk about right at the end about what the limitations are. And so if you compare the contours of state parameter that I just showed compared to those contours of clean sand equivalent that were derived based on liquefaction case histories, you can see a tremendous similarity between the shapes. So this sort of correction that we use for clean sand equivalent essentially has this sort of theoretical background that state parameter and critical state soil mechanics would provide. And again, you can see here that I put they're mostly young, uncemented silica-based sands that are essentially normally consolidated. So this was all written up some years back by myself in 2009 in the Canadian Geotechnical Journal to sort of identify this commonality between the two, is that you could use this clean sand equivalent normalized cone resistance essentially as a measure of state parameter. So the recommended quality control criteria using CPT is really to use a clean sand equivalent, and that allows you to apply it to a wider range of soils, not just clean sands. However, to do this, you need a pre-agreed method to calculate it. There are a number of different ways. I've shown you the Robertson and Ride one, which is based on IC. Now, Idris and Bollinger, and then Bollinger and Idris have also used that approach. They've suggested that you do the correction based on fines content, but then they give a link between fines content and IC, so most people still use IC. So they're slightly different. They're not much different in their end result, but they are slightly different. And so if you are going to use a clean sand equivalent, you need to specify how you're going to actually calculate it. What it also means is you can't present a simple line on a diagram of cone resistance versus depth and say, you have to exceed this number, because it depends on the IC of the soil, which is site-specific at any given location. And so you need software to process the data, and I'll illustrate that. So let's give you some examples. Here's an example of a nice clean sand, and this was published by Massage and Felenius in 2002, and it's from a clean hydraulic sand fill from Hong Kong for the Hong Kong airport. And so here's a plot of tip resistance. So the tip friction, they actually didn't have pore pressure for this sounding, but I'm using the software where it gets plotted. And then friction ratio. And you can see it's a nice clean sand. Friction ratio is constant. Tip resistance is relatively low. And then they did vibro-compaction. You see the tip resistance has gone up. So everything seems to be working. And if you look at it in terms of normalized cone resistance, the red line is the normalized cone resistance before, and the blue line is after. You can see significant improvement. Friction ratio hasn't changed very much. And so if you look at the clean sand equivalent, because it's a clean sand, there's not much difference between the clean sand equivalent and the normalized cone resistance. And so if you had a criteria based on a clean sand equivalent of 100, that's exactly the same as the normalized cone resistance of 100, since this is a nice clean sand. So it really wouldn't have mattered too much here whether you use just the normalized cone resistance or the clean sand equivalent, because it's all clean sand. But unfortunately, that's not always the case. And so here's continuing that example. Here is that cone resistance versus depth. The black line is the measured one before, and the red line is the criteria based on a clean sand equivalent of 1. The reason it's not a straight line, is a slight curve, is because of varying soil unit weights. But you can see if I actually draw the simple straight line on there, it's very close. So you can see that in the ideal cases, if you do have clean sand with a constant water table and a reasonably constant unit weight, a simple linear criteria can work and would be sufficient. But we don't always have that situation. So here's an example with a more complex profile. This is a project I was involved in here in California. And so the profile is a little bit more complex. It's mostly clean sand down to around 18 feet, and then there's a zone of interlayered sandy silt down to about 32 feet, and then more clean sand below. And so you can see the red is before and the blue is after, so the vibrocompaction has done a reasonably good job, at least in the clean sand. But in this interlayered sandy silt, you can see it's struggling a little, or appears to be struggling, because the tip resistance is not changing that much, although in this sandy layer you can see the tip resistance goes up, but in the silt layers not so good. And over on the right hand side you see the soil behavior type index, and you can see that it's a very low number in the clean sand, and then gets higher into the silt region. It actually exceeds 2.6 for a certain period of depth, and then there's a clean sand layer and then back into the silt again. So in these complex profiles it's a little bit more difficult. And so if you look at the process data, the normalized cone resistance, so the one on the left is just the basic normalized cone resistance, and if there was a criteria of 100, which works fine in the clean sand, but it doesn't work well in the silt. You can see that after ground improvement it appears to imply that, that the soil has not been improved. But if you look at it in terms of clean sand equivalent, because of the higher fines count or the higher IC value, the clean sand equivalent gets pushed over, and so it shows that the vibrocompaction was effective even in the siltier regions in terms of that criteria. It just about makes it. So here's another way to look at it. So if this was for a liquefaction problem, and so you know, the software SLIC, which is the CPT-based liquefaction software by geologist Mickey, it has a feature where you can look at ground improvement, and so it takes the cone profile and then works backwards through the liquefaction. And so for this design earthquake, it's essentially the same as picking a clean sand equivalent of 100, and so it works backwards, and now you can see that there's this variable criteria as a function of soil type. And so where IC exceeded 2.6, it's not showing a criteria, because in terms of liquefaction that was considered not susceptible to liquefaction. And the one on the right is after improvement, and you can see that the measured cone resistance always exceeds the criteria based on that liquefaction, which is essentially a criteria of a clean sand equivalent of 100. Now, one of the things you may have noticed is that here we are back at that profile, this sort of complex profile of clean sand over interlayered sandy silt. And so this is normalized cone resistance and normalized pore pressure. And two things to note is that notice that the normalized pore pressure, before ground improvement in this silt layer, the pore pressure was highly positive, and then after ground improvement, the pore pressure essentially went slightly negative. So it's indicating that there was some improvement in this lower silt, not so much reflected on the tip resistance, but very much reflected in that change of pore pressure. And I'll show another example at the end to illustrate that point. But what I do want to illustrate here is you can see that the profile of IC has changed. There's actually been a decrease in IC from before compaction to after. And the reason for that is when you see it in terms of the soil behavior type chart with the normalized cone resistance parameters, you can see that if you've got a clean sand, you have, say, a lower cone resistance or a lower clean sand equivalent, and then after improvement, of course, you've densified it, so the cone resistance goes up, the normalized cone resistance goes up, so the data moves upwards in the chart. And of course, keep in mind that IC is diagonal contours here, so you can see the IC has decreased with ground improvement. And if it's a silty sand, it also decreases, but not quite so much. In other words, you can see these contours are contours of state parameter, or in this case, clean sand equivalent. And so you can see that when you do ground improvement, typically the data moves perpendicular to these contours. In other words, you're improving the ground's becoming more dilatant and more resistant to loading, and therefore has a higher clean sand equivalent. And so IC drops. So it's nothing to get too worried about, at least for the generally sandy soils, that IC has changed. Obviously the soil hasn't changed in fines content, but it has changed in its behavior. And so that soil behavior type index IC is an index of behavior and not a direct measure of grain size or fines content. So it's nothing too much to get concerned about. The one area where it can be a problem, and it's illustrated here, is that if you had specified an IC of 2.6 as the cutoff in your analysis. It said, well, you only need to do improvement where the soil has an IC less than 2.6, and you don't have to improve it when IC is greater than 2.6 because it's more clay-like. Sometimes you can get a situation where you've got a clay silt where the IC might be slightly higher than 2.6, and then after ground improvement, because of the vibration and the induced stress history and horizontal stresses that you've imposed on the soil, the cone data does increase and it moves perpendicular to these contours of state parameter. The data now moves to an IC less than 2.6. So sometimes that can frighten people by saying, well, it wasn't susceptible to liquefaction before, but now it's susceptible to liquefaction afterwards. Of course, that's not true. Its susceptibility to liquefaction has improved. It's just that it's crossed this boundary of 2.6. And that's mainly because of this influence of stress history and horizontal stress. The higher horizontal stresses have increased both the tip and friction, and so therefore the data has moved perpendicular to these contours and it's crossed that line of 2.6. The fines content or the susceptibility hasn't changed, it's just that it's got higher horizontal stresses. And so how do you get around this? And one pragmatic way, and the software Slick allows you to do this, is that you can actually adjust the IC back to its before value. And so you can see that's what's being done here. There's been a shift in the IC of about 0.3, and so now the before and after IC is much closer, particularly up in the clean sand. Of course, there's some variability through the interlayered sandy silt. Now, the reason for that is if you go back to the basic soil behavior type chart, I can actually draw contours of the normalized friction ratio, this friction resistance divided by the vertical effective stress. And so you can see that these are diagonal lines with very low values down in the sensitive region and then very high values up in this sort of soft rock region. And so going perpendicular to those red contours is increasing in stress history. So you can imagine the sleeve friction measured by the cone is directly a function of the horizontal stresses around the cone. Now, that's not directly K0, but it's influenced by K0, so it's an indirect measure of it. And so you can see that by moving diagonally up to the right, you're increasing in stress history and horizontal stresses. So that's what part of why the reason when you do ground improvement that imposes some stress history and increases the horizontal stress, the data has a tendency to move up and diagonally to the right, which is an improvement. So everything I've said so far is really based on its application for a wide range of sandy soils, but primarily sort of young, uncemented, silica-based sandy soils. And so what do we do if the soil is not strictly in that category? And so I use this sort of generic term of unusual soils. What I mean by that are soils that have some microstructure. And the primary features of microstructure tend to be things like cementation and aging. So as soils get older and or cemented, they develop some microstructure which tends to make them somewhat stiffer and stronger. And so what we know is that the cone penetration resistance is mostly a large strain response, which is sort of more controlled by the peak strength, whereas the shear wave velocity is a very small strain response controlled by the very small strain stiffness of the ground. So by measuring both of them, through tests like the seismic CPT, you have the potential to identify these sort of unusual soils that have significant microstructure. And the way to do that, we had first suggested this about 20 years ago, and then Schneider and Moss had sort of added more data to it. And I liked the format that Schneider and Moss came up with. And they came up with this parameter that they call Kg, which I sort of refer to as, it's essentially a normalized rigidity index. Rigidity index is this G over Qt, or Qn, I'll describe in a second. So it's the small strain stiffness to strength reflected in the cone resistance. So G over Qt is this essentially a rigidity index, the small strain rigidity index, and Kg is essentially a normalized form of it, of how this rigidity index varies with the state of the soil reflected in the normalized cone resistance. And what we know now is that most sort of, quote, ideal soils, these are young, uncemented, predominantly silica-based soils, then most of those tend to fall in this fairly narrow band where this kg of varies between about 100 to 330. And so Snyder and Moss essentially had suggested that if kg, I've called it asterisk kg because it's the net cone resistance, it's a small detail, and that G0 is the small strain shear modulus that's directly determined from the shear wave velocity. So the shear wave velocity squared times the mass density, which is the unit weight divided by gravity, gives you the small strain shear modulus. So the stiffness to strength ratio, this rigidity index. So if kg is greater than 330, then generally you have soils that have some significant microstructure, for example, cementation and or aging. So the data tends to move diagonally out. And so this becomes very useful. It's a very useful way of, first of all, determining are your soils sort of ideal, of which everything we've talked about before is going to work quite well, both the ground improvement and, of course, the use of CPT for quality control. So if the data plots below this 330, where most young uncemented silica-based soils tend to plot, then everything's going to work just fine. If the data plots outside that, where this kg is greater than 330, then the soil likely has some microstructure, and you need to sort of evaluate what the source of that is. Now, if it's aging, then obviously geologic background gives you some insight to that. But for sites where ground improvement is being done, often they're relatively young deposits, but they might be slightly cemented. And so if the data fits outside here, then there may be some cementation. And what that means is if you do some ground improvement, either vibratory or dynamic compaction, there is a risk that you're actually going to destroy this cementation. So what will happen is the data will tend to want to drop back into this zone. And so not only will you remove the microstructure and sort of this rigidity index will drop a little bit, but there'll also be a drop in the normalized cone resistance. And so there's been cases where people have observed either a slight drop or almost no change in the cone resistance after ground improvement, even though they see surface settlements. So there have been documented cases where, particularly sites where there's calcareous sands, where there's some light cementation, and so, of course, the ground improvement destroys the cementation, and the tip resistance doesn't appear to change very much after ground improvement. But with time, it quickly picks back up again. And so that's reflected in this other feature that we often see, these time effects of compaction. Here's a very well-known diagram from Mitchell and Solmar from '84, where they did some ground improvement in Africa. And they showed a very significant time effect that Wayne Charley, Professor Charley, had done this nice diagram of the cone resistance at n weeks compared to the cone resistance at 1 week, showing this improvement with time. So the relative change in the cone resistance as a function of time. And you can see after 10 weeks, it can vary from as little as a few percent to as much as 100%. And in fact, Professor Charley actually suggested that it was a function of temperature. When you got into warmer climates, there seemed to be this bigger time effect. But that may simply be a fact that in warmer climates, you tend to have somewhat different mineralogies in the sands, and also you have more rapid aging and cementation effects that we observe in warmer climates. So although there appears to be a temperature effect, it may in fact just simply be a feature of the rapid redevelopment of this microstructure that was destroyed by the ground improvement. And so it's really useful, if you can, do seismic CPT, get the shear wave velocity and the cone resistance at the site prior to designing the ground improvement to first of all determine whether or not your soils have some microstructure and how that may be influenced by the ground improvement. And of course, it can be cases where you may do initial ground improvement, and in the short term, the cone resistance or any test may go down a little bit before it starts to build back up again with time. And it's a function of what the microstructure is, whether or not it's due to the mineralogy, such as carbonate sands, or whether or not it's just simple cementation. And of course, the reason carbonate sands tend to be more problematic is that they tend to cement up rather rapidly, and they also tend to be very compressible. So those two things often combine to show very little change in cone resistance once you do ground improvement. And so sometimes in projects in the Middle East where they've got carbonate sands, they've sometimes done two passes of ground improvement, one that originally broke down the microstructure and caused a lot of surface settlement, and then the second one to densify even further. So there are additional measurements, and one of them, of course, is the pore pressure, which I mentioned, which is very useful in more fine-grained soils like silts that can capture the stress history, and I'll show you another case history in a second. Of course, the other is shear wave velocity. I've talked about it in terms of identifying microstructure, but others have suggested that you can use it as a way of capturing stress history, or as a way of measuring the average increase in soil stiffness, particularly if the goal is to improve settlement characteristics of the site. So you want the stiffness to go up, and so shear wave velocity can be a direct measure of that. The challenges is that the shear wave velocity tends to be a rather insensitive parameter because you square it to get the stiffness. And so you need rather high accuracy if you're going to do that. And then if you're doing ground improvement that puts inclusions into the ground, you've got a scale effect of exactly over what distance do you measure the shear wave velocity to get some average stiffness. But there's a fair bit of work going on in that area right now, and I suspect we'll see some further developments there. But right now, things like the seismic CPT to measure the microstructure is certainly recommended. Then there's also the use of the flat plate dilatometer, because of its slightly increased sensitivity to horizontal stresses, and I'll illustrate that by an example. So first, here's an interesting example. You know, Professor Campanella and I published this quite some time ago, over 30 years ago, and it was a site just outside of Vancouver in an area called New Westminster, and it was a site of hydraulically placed fine sand. But during the placement of the hydraulic fill, they actually did develop a fairly significant thickness of uniform non-plastic silt in one portion of the site. And they were evaluating different ground improvement. This one was dynamic compaction. And so you can see that the dynamic compaction worked quite well in the clean sand above, but in the silt, it looked like it didn't seem to be that effective. So the tip resistance only went up a little bit. But if you look at the pore pressure before dynamic compaction was very high and positive, and after dynamic compaction, it was actually slightly negative of hydrostatic. So that's reflected in this BQ diagram on the right, where you can see a big positive BQ before compaction and then a slightly negative one afterwards. And we did get a sample of the silt and we tested it, and there was a significant improvement in both the undrained strength as well as the cyclic resistance ratio of the silt due to the dynamic compaction, even though the tip resistance didn't change very much. But interesting enough, if you plot that data in terms of clean sand equivalent, there is in fact a significant increase of clean sand equivalent in that silt layer. So both the clean sand equivalent and the pore pressure both support that the silt was in fact improved, mostly due to the I think the effects of stress and stress history imparted by the dynamic compaction. And then here's an interesting plot. Professor Marchetti just recently published a paper this year suggesting the idea of the combination of the CPT and the DMT was a useful way of looking at the effects of the improvement of increased horizontal stresses. So we have this classic plot of the cyclic resistance ratio against the normalized cone resistance clean sand equivalent. Here he's showing the Idris and Bollinger line in dashed. And then he's saying that the KD parameter that you get from the DMT actually produces sort of contours that overlay those, so that for a given cone resistance, if the KD is relatively small, then you're okay to use the basic cone curve. But if KD is high, it's picking up the more beneficial effect of stress history and horizontal stress and showing you that the resistance has increased. There's very little documented case histories to support this yet, but certainly the concept is sound and shows lots of promise, and probably you're going to see more of this in the future, where after ground improvement, the possibility of doing a limited amount of DMT in combination with the CPT may help you quantify the additional improvement, particularly in the siltier material as opposed to the clean sands. Now, just to finish off, I've talked mostly about compactability using vibratory techniques, predominantly in sandy soils, but in more complex soil profiles where there's a lot of fines, or in more fine-grained soils, soil mixing is also becoming very popular. And so you'll see a lot of soil mixing in fine-grained soils, and people wanting to use CPT for quality control criteria. And the traditional quality control criteria for soil mixing is often unconfined compressive strength. But of course, people realize that it's very expensive and very slow to drill, try and take samples, then take them back to the lab to measure the unconfined compressive strength. And so people are increasingly wanting to use the CPT, and what we realize, of course, is the undrained strength is just the unconfined compressive strength divided by 2. And so if someone specified a criteria in terms of unconfined compressive strength, you can just convert that to undrained strength and then use the CPT as a very simple, repeatable way to measure that undrained strength. And so at the bottom here is an example. If the criteria was, say, set at 2 atmospheres or 2 bars or 0.2 megapascals or 2 tons per square foot for the unconfined compressive strength, then that means the undrained strength has to be greater than 1 atmosphere, which means that the cone resistance nominally has to be greater than about 15 atmospheres. You may remember from that soil behavior chart that, of course, we can often push cones into soil in stiff clays with cone resistances of up to 100 atmospheres. And so it's not that difficult to push the cones into a lot of these soil mixed profiles, as long as there isn't too much cement in the mixing, and that the unconfined compressive strength doesn't get too large to make life too difficult. And so increasingly you're seeing the CPT being used as a QC criteria for soil mixing. So in summary then, CPT is becoming really the most common in situ test to evaluate ground improvement, particularly deep compaction. You know, obviously you could use it for shallow compaction, but if it's very shallow, you know, just a meter or so, then it's not always the most cost-effective way to do it. So it has become the most cost-effective for deep compaction. And the issues to look out for, I didn't really talk about it, but we've covered it in previous webinars, is this issue of thin layers, is the transition of cone data from one layer to another, and the need to possibly remove that, and that was in one of our previous webinars. But I did talk about the effects of soils with high fines content, and how I would recommend that you use a criteria based on normalized clean sand equivalent cone resistance, and that will avoid a lot of your problems. There are time effects. Those time effects, I suspect, are mostly controlled by microstructure, and so the need to identify whether or not your soils have microstructure, and I briefly illustrated how you could do that with something like the seismic CPT, where you've got the combination of shear wave velocity plus the cone data. So those two measurements, the small strain and the large strain response, give you some idea of identifying the potential for soils with significant microstructure. So that was a fairly quick review of how you can use the CPT for quality control in ground improvement, and I'm certainly happy to take any questions. So I think Kelly's been writing a few down. Let me have a look at the first one. The first one is there any experience with vibrocompaction or vibro replacement in marine environments to significant depths, such as 40 meters below the mudline? And I think the answer is yes. You know, people have used vibratory techniques over water around the world. Not that common, but there are a few examples, particularly in Asia, of where large projects have done vibrocompaction in marine environments. Now, 40 meters below the mudline, that's clearly getting to a significant depth. And so there's an issue of equipment. But the nice thing about vibro is that it can be done to significant depths with special equipment and cranes. They typically operate from barges. And in fact, I think that example I showed of the clean sand from Hong Kong Airport, I know that in some places the vibrocompaction was done over water before the platform was built. So yes, there is some examples, and of course usually what is done is that the vibratory compaction is done, and then fill is placed, and so you end up creating a dry land platform that eventually the quality control is done from. But you can certainly do CPT over water to evaluate the quality control of any ground improvement. So next question. Are these techniques applicable to complex soils such as those found near volcanic activity? And I think this is really that issue of microstructure. I talked about carbonate sands, particularly in the Middle East, where there's been a lot of ground improvement in soils that have very high carbonate contents. But the same sort of features exist in these volcanic soils where they're not necessarily prone to cementation, but they do tend to be very angular and very compressible, and they're not always silica-based in the sense that we know them. So volcanic soils do tend to be different. Actually, I said not cementation, but some of the pozzolanic volcanic soils that have occurred, say for example in Italy, they tend to be lightly cemented. So I think if you do seismic CPT, first of all identify whether or not these soils are behaving in an unusual way, that they have some microstructure, and then you need to identify the source of the microstructure, whether or not it's cementation, and then of course recognize that the ground improvement may in fact destroy that cementation as well as densifying. So you're going to get a positive effect from the densification, but possibly a negative effect from the loss of cementation, and whether or not that cementation comes back. And so sometimes people have done trial sections to first of all see if the technique works. But you have to be willing to do the trial and then monitor it over a series of several weeks to see if the time effects are significant. Someone's asked a question and said, what's that KC? And that was back on when I briefly summarized and said, how do you get this clean sand equivalent? And I had mentioned there's this correction factor. And so what you need to do is you need to go and read this paper, Robertson and Ride, that was in the Canadian Geotechnical Journal in '98. That was a CPT-based liquefaction method. And there it said that to get this clean sand equivalent, this KC was simply a function of IC. I did have a slide on this, but I deleted it for time. But basically it's a simple relationship that was developed as this correction factor as simply a nonlinear function of IC. So when IC is very small, KC is 1, and then as IC gets larger and the material gets more clay-like, KC progressively increases and you make a progressively larger correction. Now the approach that Idris and Bollinger have taken is that they do a similar sort of correction, but theirs is more additive, and they base it on fines content and say, well, as fines content increases, then you make an addition to get the clean sand equivalent. The end product is essentially the same. So have a look at that reference for that KC parameter. Then the other one is the lateral stress increase permanent after soil improvement, or will it come back to an at-rest level condition after a while? Well, of course, the answer to that depends very much on the type of ground and the type of ground improvement. But typically, the vibro techniques that I was showing back here typically impose a significant increase in horizontal stress that doesn't go away. These vibratory techniques, they're pushing the soil horizontally and they're compacting it horizontally. So the horizontal stresses tend to get locked in. So what you're asking is like, if you increase K naught, say from initially 0.5 and you say you boosted it all the way up to 1, will it stay at 1? And I think in general, yes. I mean, it's not going to relax all the way back to 0.5. Clay soils tend to creep and relax back, whereas sandy soils tend not to. And so, yes, I think in general it stays there, so the improvement is permanent. For example, if you look at case histories from earthquakes, generally wherever a site has had ground improvement, usually using vibratory techniques, they've performed well in earthquakes. So that implies that the effects have been permanent with time. Now, there is some school of thought where people are beginning to look at desaturating soils by inducing air, and in fact vibratory techniques that, like this vibrocompaction that uses air, will put air into the ground and those air bubbles will make the soil a little bit more compressible, which is part of the reason of the time effect, that in the short term the soils are actually more compressible and therefore give a slightly smaller cone resistance. And as the air bubbles get reabsorbed back into the water, the compressibility decreases and the cone resistance goes up. And so that's one of the questions related to the effect of air, is it permanent? And that's an issue yet to be resolved, but unlikely to be permanent under conditions of long-term stable groundwater conditions. So next question, how do we, what's the question here? Is it, how do we control the soil moisture? Yes, sorry. How do we control soil moisture? I'm not quite sure what you mean by that. Now, if that relates to soil mixing, now the soil mixing is a whole topic on its own about how it works, how people do it, what sort of mix is used, and usually there's some cementing agency, and so the cementing agency does influence the moisture content, and so the moisture content before of a clay could be very high, and then the soil mixing will often decrease that and create a much stronger ground. Next question. Some people believe that the fines content is enough to decide on the compactability of a given soil. How can we convince them that this is wrong? Well, maybe one way to convince them is to show this slide that Dagan showed, the one on the left. Oh, sorry, not Dagan, it's the one that Kirsch showed, is that you can see that the scatter on the plot of fines content is more than the one on soil behavior type IC. And so, yeah, I mean, at a given site, so if you're at a given site where the plasticity of the fines is reasonably constant across the site, then fines content would work okay. Problematic, difficult to do, difficult to get lots of samples to keep measuring fines content. I mean, the beauty of using IC is you get that from the cone, which is fast and continuous and repeatable. So using fines content as a criteria is problematic, which is why a lot of people sort of switch from fines content over to IC simply because of the speed and reliability and the continuous nature that you get IC. So I think maybe what you do is not to say it's wrong, but it's just not very pragmatic, and you're better to have a CPT-based system that uses IC. How do you find the value of a web-based interactive database for CPT? Ooh, okay, that's a tricky question. I think they're saying, could we have an interactive database for CPT on the web? And in fact, I have actually worked on the basic elements of it. At CPT 14 last year, the conference that we organized in Las Vegas, at the end of the conference, I did sort of say that I actually have a database. And what it does is it uses the software from geologist Mickey called CPT, which is a CPT-based interpretation software. And so what I've done is I've actually developed quite a large database of well-documented sites around the world and put that data into CPT. And that creates a nice format as a database because the software essentially compresses the file very nicely, and it gives a uniform format to look at and process the data. So it allows you to look at the data and produce overlay plots very easily, which is often what people want to do for a database. The problem with a lot of databases in the past is that often the CPT data comes in many different formats, different text formats, different spreadsheet formats, and so it becomes a bit of a nightmare to try and make all of the data into one uniform format, since most people collect it differently. And so by using the software CPT, in a way I got around that by loading it into CPT and then allowing that software to become a sort of standardized format for both processing and looking at the data. So that is available. I actually haven't put it on the web. I actually need to find a way of posting it on there. Maybe one of the best ways to do is I could actually do it through the geologist Mickey and Gregg website as to post it as really a series of CPT files that you could download and open with the software that has these documented sites on there. I think one of the things that slowed me up a little bit is really how do I put together the background documentation, because there's quite a number of sites, and other than just simply give you a reference and say, well, if you want to know more about this site, go and read these papers. That's what you'd have to do. But so far I've clustered them together by soil type, like soft clays, stiff clays, sand sites, interlayered sites, residual soils, and soft rocks. So I have a fairly large database. I'm still working on it, but generally if you send me an email, I'm more than happy to share it. But you do have to go and get the software. But the nice thing about CPT is it's a very inexpensive software. It only costs was 199 euros to get it, and you can download a 30-day free trial from the Geologist Mickey website. So if you just type in Geologist Mickey, and it'll pop right up on the internet, and you can find it. Next question: can vibratory compaction be used for offshore deep foundations? Ooh, greater than 1,000 meters below the seabed. Ooh. Greater than 1,000 meters, I doubt it very much. That was the first question, was, can you use vibratory techniques offshore? And the answer was yes, but there is a bit of a depth limitations, both in water and in soil. And vibratory techniques, as you saw from the photographs back at the beginning, they're typically crane-mounted devices where you've got a vibrating probe that you lower down into the ground. And so clearly there's a limit to the length of the device that you can lower down. So basically the water depth has to be shallow, and of course relatively shallow depth below mudline, up to 30 meters or so. But once you get into deep water, no, life's a little bit more difficult. There is the potential for seabed devices, but to my knowledge, I'm not aware of anybody that's done that in very deep water. Next question: where did the cone factor 15 come from for deep mixing? Well, go back and look at the webinar that dealt with fine-grained soils, and we talk about how you interpret CPT in clays, fine-grained soils, and in there you'll see that there's this reference about how to get the undrained strength using this cone factor, and that the average value is about 14 or 15, and so that's where that number came from. It's also written up in the CPT guide, so there's lots of documentation that supports that number. But the CPT guide, which you can download, is a good starting point, as well as looking at that previous webinar. Any experience on pumice sands, and that links back to that question about volcanic sands. Yes, there is experience. The ones I'm aware of were from Italy, where they've got a number of volcanic sands, and they've done some ground improvement. But as I said, these pumice sands, they tend to be compressible and cement very easily, and so they have a lot of microstructure, and so you really have to be aware of how that influences the results. And so what pumice tends to be grains that have internal voids, so the grains themselves are very compressible, and they tend to cement against each other. So they're analogous to these carbonate sands of the Middle East, which are also very compressible and also tend to cement very quickly. And there's been lots of experience of vibratory compaction in the Middle East, and they had difficulties, and that's mainly because the vibrocompaction initially destroyed the microstructure, and then also caused a lot of crushing. Now, there was significant ground settlement, so there was significant improvement, and certainly the buildings that were founded on these sites have performed well because of the ground improvement. So yeah, you could look at the experience on carbonate sands as your background for these pumice sands. Can you use CPT or seismic CPT for settlement estimates? And the answer is yes. In fact, we had a webinar on that. We had a webinar on seismic CPT, and one of the things we talked about is how you would do settlement estimates using shear wave velocity. And also, I think we certainly talked about how you could estimate modulus for settlement calculations based on some of the other webinars as well. So Kelly and I realized that we haven't done a webinar for a while, and so you need to go to the Gregg website and look back over some of those recordings, because there's a lot of useful information. And other question: can the software Slick apply the IC correction before and after ground improvement? Yes. So SLIC has a dialogue of advanced parameters, and if you scroll right to the bottom, there is one that actually says, do you want to make a correction to IC, this delta IC, and you put in a number, and what it does is it just shifts the IC over before it does the liquefaction analysis. So yeah, it's in that software. Another question, how can you improve soil with swelling clay? Ooh, wow, that's beyond this webinar. This webinar was focused primarily on quality control for ground improvement, primarily vibrocompaction. So I did talk about soil mixing, but really you need to talk to a ground improvement expert on how you might do usually soil mixing on swelling clays. But yeah, it's possible, but you need to talk to an expert on ground improvement about that. Next question, do you recommend certain CPT locations with respect to locations applying vibrocompaction? That's a good question. So vibrocompaction is usually laid out on a grid, either a square or rectangular grid. And traditionally, CPT is being done as a quality control in the weakest portion of the grid, which is between the grids. So for example, if you had a triangular layout of stone columns or vibratory compaction, CPT is typically done in the middle. Now that is the weakest location, and obviously therefore is more conservative. And there is a trend now towards doing either a number of different locations and taking an average, or picking a spot that's not quite as conservative as the spot furthest away from any of the ground improvement. And so there's a trend to do it either directly between two vibratory points, or some people actually are suggesting to do it at the 1/3 point, which is a third of the way between two vibrocompaction or stone columns, so that it's not quite as conservative as going to the weakest point. But it's up to you, and in the end, it's how you want to apply the criteria overall and what the problem is, whether or not it's liquefaction and so on. So it really depends on what the design objectives are and how you want to apply it. And another person asking about how you get to choose the NK value. Well, NK of 15 is a good start. If you want to check it, you can verify it against some samples as a site-specific. The difficulty there is most people do samples and unconfined compressive strength, and they typically have a high scatter, and so you often don't get much improvement. The ones I've been involved in, people just essentially become conservative, and they use an NK value that's a little on the conservative side. So I was suggesting 15 as sort of an initial, slightly higher than the average value of 14, but some people have actually gone as high as 20 and said, well, we'll just use a simple number like 20 and just build in a little bit of conservatism in that conversion. So what's the suggested procedure to design the quality control of a soil deposit based on CPT? Okay, well, assume that you go out and do a site investigation first, which is how you've determined you need to do ground improvement. And hopefully that site investigation has involved CPT, and hopefully it's involved seismic CPT, so that you've verified whether or not the soil has some microstructure, you've verified what its current condition is, and you've also determined what you would like it to be. In other words, what criteria is driving it. Is it a criteria based on increased resistance to liquefaction? And so, for example, if you're using that liquefaction resistance, if you're using the software SLIC, SLIC does have that feature that I mentioned and illustrated, where there's a button on the software that allows you to actually determine what level of cone resistance is needed by working backwards through the system. Here it is, here illustrated on the slide. So for a given design earthquake and a given factor of safety, so by increasing the factor of safety slightly greater than 1, you're reducing post-earthquake settlements. And so the software will actually go in reverse through the liquefaction analysis and determine the profile that you need to achieve. So it'll identify the regions that need improvement the most. So here is an example before ground improvement, the red line illustrating where the ground improvement is needed. So it's not needed up near the surface, it's needed down at depth. Of course, in this case, it's sort of showing it's needed down around 35 feet, which is down around 10 meters. And so if it's liquefaction, one of the issues you might want to think about is whether or not you really need to improve the ground down there, and that's an issue of how you're running your liquefaction analysis. In fact, Kelly and I were talking that one of our next webinars should be really an updated webinar on liquefaction, where we do worked examples using the software Slick to sort of talk about some of these advanced features and how you would do it. And one of the advanced features is how you cope with possibly weighting the analysis as a function of depth. But Slick would be a good way. And then you just work your way backwards, and in this particular case, it was in essence a clean sand equivalent of 100, and that would be an easy way to specify. And if it's liquefaction, you might say, please improve the ground so that the clean sand equivalent is greater than 100, and that only applies when IC is less than 2.6, and then tell them how you want the clean sand equivalent calculated. So that's how you would go about it. Last question, when you mix soil with cement, you have a thermal reaction, temperature goes up, can this influence the CPTU data? And now in general, no. Most cones are temperature compensated, and so even if the ground is a little warmer, it doesn't influence the results. There is a slight transient effect. If you were to go from very cold ground to very hot ground, there'd be a slight short-term transient effect, but that usually only takes a minute, so you either stop and pause and let it come to equilibrium for a minute, or that it wouldn't have much effect. So yes, in general, the thermal reaction doesn't affect the cone data itself. It may affect how the ground itself is responding, which is a time effect, but it's not affecting the cone data at all. Okay, well, hopefully you found that useful. Some of the questions were quite insightful, and hopefully they were helpful. And so hopefully you found this informative about how you might want to use the CPT for quality control for ground improvement, particularly deep compaction. So that concludes this webinar. Our next one, which we'll plan early in the new year, I think I want to do one on sort of an updated soil classification system. I'm working on it right now, working on a paper related to it, so I'm quite keen to share that with you and to go through some worked examples of how that would work. And certainly a key element is something I sort of gave you an early look at, was using shear wave velocity, this curve here. So it's going to show you this plot and how to use it along with the other plots as well. So we'll do that in the new year, and also I think we'll do one on sort of advanced features of liquefaction analysis, because I've done a number of presentations to small groups illustrating some of the details of the software and how you use them and make full advantage of some of the software. So hopefully you found that useful. Thank you for attending, and we look forward to you attending the next one. Thanks very much.